Yes, hello together. Um, on this rainy morning, I just want to recommend that, yeah, maybe some normality is coming back and our university is also running. And especially our faculty is running. And after Eastern, there's the first event. And if you like, you can, yeah, call my colleague down here, and it would be nice if you would participate. I will try the 10 kilometer. I'll see if I make it under 1 hour. I don't know. I've been running 10 kilometers. This is 3 years ago, for 3 years in the past for me. And another thing, I think just yesterday you got an email that the Bremer Philharmonics are coming to our university on Sunday, and this is really a nice program with Mozart, Haydn, and Beethoven. I also think, although I'm yeah away this week, and maybe I come a bit earlier in order to join this really nice concert of the Bremen Philharmonics. And here I think one drink and €5. That is not too expensive. Okay, but then we are going to the lecture. I have to open it, and we will do the exercise today. There we are. Statistics and lecture. So first of all, there was one left from the last time. This was exercise 5. I'll just copy it. And we are here. No, there. I'll have to do another one. What is my computer doing now? Yes, it is. Here it comes. Okay. Here we are. Okay. And nope, that is wrong. This one. Copy and paste. Here we are. This was B. We have a randomly distributed variable with expected value mu is 10 and standard deviation is 2. Assume that the yields of 2 different years are statistically independent. What is the probability that the yields of 2 following years are at least 8%? So here we go. We have x is distributed 10, 4, 4 because you have n of mu sigma squared. And what we want to have is B1, the probability of P of x is larger than 8 for 2 following years. What are we doing in order to calculate this and not just type it in some statistics software, but what we want to do? And for this, I always draw the diagrams. F of x, mu is 10, and normally distributed, so it looks more or less like this. And then we have the 8 is here. So what we are looking for is the area from 8 to infinity under this density function. And how do we get this? We have talked the last time about this. Standardization means that is x minus mu over sigma. So we want to translate this again into the normal distribution of standard normal distribution of then some part here. So the 10 becomes the 0. And what we are interested in is this limit, this lower limit. So in which number translates this 8, because we are now interested in this area and these two areas coincide. How do we get the number which coincides for the 8 of our specific distribution translated in our standard normal distribution? And the standard transformation is just given by z. This is the value we are interested in, and this is our value from our random variable. -1, great, because you just put in that is 8 minus 10 over 2 is, of course, -1. So, and this means we can again type this in Excel or another software, but I also want to show you, because in the exam then you can do it via your calculator. I think I will give you also the opportunity to use Excel, but also to look it up in some table. Therefore, I have to open the table. Here we are. So my new software. Takes some time. Normal distribution. Here we are. So we are interested in -1 in our table, which number we have to look up. Because in this table we don't find -1. We look up, of course, 1, and the reason is we have here symmetric distribution. And therefore we know that this area here is as large as the area we are interested in. Therefore, we look up -1 again. And here I can also put this in and paint there. So where it is here. So we look up the 1, the O here, this is the second digit. So we obtain 84%. So then we know that phi of 1 is 84%. And now we are interested in 2 times the yield is larger than 8%. Of course, we now know that this equals also P of X is larger than 8. And then the answer is P of X larger than 8 squared, because the events are statistically independent. And so we obtain 0.84 times 0.84 should be something around 0.7, I think. Let me open also some Excel file for this upload. Here we are. A1, we call this. So you can see, no, you can't see the Excel. To switch to the other monitor. Here we are here. Bit smaller, and then we go in here. Can you give me back that you are seeing the Excel file? Okay, great. So let's do it also here within Excel, because what do we need? We need equals normally word, and now we can say it's 8 semicolon 10 standard deviation 2 and cumulated is true in German var, and this should end up with, now we get the other way around. H2, then we have to take 1 minus, and then we are at the 8,4, and this squared. 0.7 is quite good. Okay. So, and this is then just using our this is then just using the syntax of Excel. Can you give me back that you got it? Why do I have to put in here the 1 minus cumulated distribution up to 8? Because what area gives me this syntax back if we go in here? And this, if you want to use Excel, this you have to practice then, because of course, let's take green here. 8, if we calculate with the statistics software, then this gives us back the cumulated area from minus infinity up to 8%. But we are interested in this area, and therefore you have transformed your 16% in 1 minus 16%. And this is, yeah, that is not really hard to do, but you really have to practice it. And I think if you always have in mind these diagrams, then you are really knowing what you are doing. And this is the alpha and omega in statistics, not only pressing enter. Anything comes out and you say, well, of course it's significant or whatever. You really have to know what you are doing and how to interpret your results. Please keep this in mind. So, therefore, we obtain here 0.707 is roughly 71%. So this is the probability that 2 times in a row we have more than 8% yield of our bond, or what else you interpret your investment up here. So then the next one. 2. What is the probability that the yields in the next 10 years will be exactly 3 times less than 11%. Of course, the first question we have to answer is what is the probability of a single event that our yield is less than 11%. So x, oops, x is less than 11%. Well, I didn't write the percentage sign, so I leave it out in this case too. So how do we obtain the probability of x is smaller than 11? What are we doing? In our diagram again, 12 f of x, x, which area we are interested in. Hmm? So if you do it verbally, almost nothing will be recorded via my micro. I just tried it. Or just type it. Say, do we are on the left side or on the right side? Sorry, this is my clock. I think my son just played around with it. On the left side, great. And then we put in here the 11, and this is the area. Again, if we go to the standard distribution, we are interested in this number here. What do I have to write at this limit? So this equals, and the probability of that is, oops, that is smaller than what? 0.5. Great, because we just write here that is 11. Oh, here I did something wrong, I see. You have seen what I have done wrong? This 12 here, or, sorry. This 12 has to be 10, of course. So I take the rubber, 10, and then this is also not right. But this is not bad, because then you see that I am doing something wrong. And I think you also keep in mind what we are really doing. So, and now we have 0.5 here, and this 0.5 comes from, that is 11 minus 10 over 2 is 0.5. This again we can look up in our table. 0.5 is over here, so we are roughly at 69%, and right now we are really interested in this number. We don't need any 1 minus or something like this. So this is roughly 69%. So, but now we have 3 times out of 10. So what we need is now how many possibilities of 10 events do we have that 3 of these events have a yield less than 11%. So this could be the first, the second, and the third event. This could be the first, the second, and the fourth event, the first, the second, and the fifth event, and so on, and so on, and so on. But we have a formula for that, because one of these Bernoulli guys did this for us in the 18th century. These are the so-called binomial coefficients. So this means that there are 10 over 3 possibilities that 3 times the yield is less than 11% out of 10 events. And this is then 10 faculty over 7 faculty times 3 faculty. And now out of 10 means, of course, the probability of x smaller than 11 to the power of 3 times 1 minus probability x smaller than 11 to the power of 7. This you know from the binomial distribution. So, and this I will do in Excel again. Then we need equals faculty, oops, 10 equals faculty 3. But of course on your calculator you of course have also faculty and 7. So we need is this over this times this is 120, and we need equals Norm inf, no, word 11, 12. Oh, this is this. Where's my mice? Display. Here it is. So 11 semicolon 10, 2, cumulated 69. Great. So we need is 69 to the power of 3 and equals 1 minus 69 close bracket to the power of 7, and then we take this times this over times times 120 is roughly 1%. So we obtain then this is 120 times 0.69, 0.31 to the power of 7, which is roughly, what do we have, 0.105, 0.0105, roughly 1.05%. So the last one, C, there I need a new one. Oopala. Save this. Oh. Save. Copy. And we take C. Which yield can be maximally expected with a probability of 99%? At a first look, this seems complicated, but again, think in the diagram. What we want to calculate is just again our diagram, f of x and 10, 99%, so we will be somewhere here. And now we know that this area is 99%. And then we ask, which x here coincides with the area below the density function of 0.99. Well, and therefore I told you, you should have in mind some specific numbers of the standard normal distribution, because this just means, oops, my monitor is not there anymore. There it is back. Okay. So standard normal distribution we just learn these numbers 0.99. For this we can go in our table 99. We are around 2 point here 2.33 is more or less the value which we need for 99%. And this I gave you also in the lecture. If we go up, uh, here we are. No. Where did we had it? Up here. So why is it from this picture 2.33 and not 2.58 where we have the 99? Well, the reason is very often we are just interested in a symmetric interval, some hypothesis, is it true up to a significant value of 99%. So this 2.58 here coincides that we are not going down here to minus infinity, but we cut the interval here. And then if we want to have, when we just come from the left side from minus infinity until some specific number, and this area should in a whole be 99%, then of course we need this missing area of 0.5%. So we know that from here to here we have this additionally 0.5%, and up to here we are then from the whole left side by an area of 99%. But actually all these properties of the normal distribution you should already have seen in your introductory courses. So we can then say that this value is 2.33. Then what is x? So p of z smaller than 2.33 equals 0.99. 9. How do we obtain x? Because we are interested in this number. Now you have just think the other way around. So now we come from the value z and we want to know x. In the other questions, we had the value x and we calculated for the standard normal distribution z in order to look it up in the table. So the formula is again x equals, not x, sorry. That equals x minus mu over sigma. But now we know z. Then we have sigma z plus mu equals 2 times 233 plus 10 equals 14.66. So the maximum yield is 14.66%. Got it? Again, you really haven't talked in that way about the standard normal distribution in your introductory courses. Anyway, we will go on in this because all this, of course, and then exchanging the standard normal distribution with other distributions, we will do if we're talking about confidence intervals and hypothesis testing. Okay. Then we are going to estimators. Mhm. This we don't need. Cut it. And let's start. Here we are. Then let's take the first. So. No, I don't want to have take new designs. I'm always annoyed when software suggests me anything because I want to do it by my own. So, first of all, unbiased estimators. What was the property of unbiased estimators? Let's look it up. Unbiased estimators, we had that, not asymptotically, that the expected value of our estimator equals the true value of the estimated parameter. So then we just write down the definition of an unbiased estimator for one. Our estimation function should be just the sum of our n random variables with some weight of AI in front. How do we call such an estimator? If you heard my macro course, within my macro course, we just used such an estimator. This is just a weighted average. Think of inflation, the consumer price index. There you have 100, 200 goods, and then you weight every good with some number. Milk, 1%. Washing machine, 8%. And so on, and so on, and so on. And all the weights, of course, have to sum up to 100%. And nothing else we have here. And now we want to see if such an estimator is, so to speak, a good estimator. Is it unbiased? And therefore we just put in expected value of sum I1 to n I AI times xi. And what we use now is the properties of our expectation value operator. What is x of x plus y? Which property has this operator? I think in the second lecture also I recapitulated the properties. X and y are statistically independent. Then we can say E of x plus E of y. And therefore, we can move in this expectation value operator into the summation. And what else we know? A times x. This, of course, means also that we can take it out because it's a linear operator. So A times E of x. And this means that we can write this. Let's do it very slowly. 1 E of AI xi equals sum I 1 to n AI E of xi. And what is the expected value of our statistically independent random variables xi? Well, this is just the expected value mu. So we obtain, and it is the same u, of course. All the xi's are drawn from the same distribution. and therefore we obtain sum AI times mu. Well, and here no index I anymore, and therefore we can put this mu in front of the summation. So this is then mu sum I to 1 n times AI, but we have sum over all AIs equals to 1, and voila, the expected value of this estimator equals our true parameter of our distribution. Second, this, I think last time I saw it already. This has to be k over n. I have to change it. So, number of successes, k over n, is unbiased estimator for P for binomial distribution. So why is this? Of course, we could also now calculate this taking the binomial distribution, taking the expected value, but we already have calculated this property here. And what is k over n? K over n is just the arithmetic mean of xi binomial distributed. Because this means we have a Bernoulli experiment and xi is just 1 for success and just 0 for not success. And if we just sum up 1 plus no, 0 plus 0 plus 1 plus 1 plus 0 plus 0, then of course, taking the number of successes over the number of events, then this is just the arithmetic mean. Let's say we flip a coin 10 times, 7 times we have a success, then of course 0.7 is just the arithmetic mean of 7 times 1 and 3 times 0. And this means since the arithmetic mean is just a weighted average, so to speak, it is a weighted average just weighting every random random variable with the same weight, 1 over n. So this is just an estimator out of this class. And for this class of estimators, we already have shown that it is unbiased, and therefore it has also to be unbiased. But k over n is an estimator out of the class of estimators of question 1, then k over n is also unbiased. And this, of course, we are doing quite often, since we do not want to calculate always the same things. We want to have some general results, and from this we have the general results that for all weighted averages we have the result and that these are unbiased, and therefore if we find that our specific estimator is element of this class of these estimators, we do not have to do the calculation once more. So, and now we come to some more interesting stuff, I think, because now we want to explain, oops, why we had in the lecture, remember that for the variance, we have this funny factor here that we do not divide by 1 over n, but we divide by 1 over minus n. And the reason for this is that with this factor 1 over n minus 1, we obtain an unbiased estimator for the variance. And this is the third question. And again, we just start with putting in the question into our definition, what is an unbiased estimator? So we take expected value of sigma hat squared is the expected value of 1 over n minus 1 sum, and now I leave out n, I going from 1 to n. I think you know that this stuff has also always to be written down here. So this is then xi minus x bar. X bar is the arithmetic mean. This I should also write down here is 1 over xi. So again, linear operator, we can take out the factor squared. So we obtain 1 over n minus 1 expected value of sum of xi minus x bar squared. So, and now this is a bit more complicated because I don't want any professional audio. You still hear me, yeah? Could you just give it back to me because I got good. Okay, so here at this part we have a multiplication. And I think from your introductory courses, you know that taking expected values from the product of random variables, then you have a problem, because then you cannot just write down expected value of x times y is expected value of x times expected value of y, because then you have to deal with the covariances. And therefore, we now, do something what we are quite often doing in mathematics or statistics. We are multiplying with 1, or we are adding a 0. And this we are doing just here, that we add within this 1 over n minus 1 expectation operator sum over xi minus mu plus mu minus x bar squared. And this we can write as 1 over n minus 1 expected value over sum xi minus mu minus another bracket x bar minus mu. So this is just our inserted 0. And now we have something quite nice, because this is our true difference we need for our true variance we are interested. Because remember, we want to show that this one equals just the true parameter sigma squared. And this is just the second binomial formula. You know, from a minus b squared is a squared minus 2ab plus b squared. We can write this 1 over n minus 1 expected value of sum over first part xi minus mu squared minus now 2ab 2 times xi minus mu times second part x bar minus mu plus b squared is x bar minus mu squared. So, and now we have 3 parts in this formula. And this part here is already more or less our true parameter sigma. And we know here we have a sum or a difference of 1 part, 2 part, and 3 part, and we know that the expected value is a linear operator. So now we can move in the expectation operator as 1 over n minus 1 times the sum of expectation operator, sum of xi minus mu squared minus 2 times e of xi minus mu, and the sum x bar minus mu plus the sum of x bar minus mu squared. So the first part here we are done. This is again a product of random variables. We cannot do anything else. Expectation value of xi minus mu squared. But within this sum here, this is a fixed number. X bar is a number and mu is a number. Again, this we can take out, and then we obtain 2 times x bar minus mu times, and now we can split again, because here again you have just a difference. So you have xi minus some mu, and this is also just a fixed number. Again, x bar minus mu squared. This is just some number. Nothing is random here. So you obtain x bar minus mu times the sum over 1. And now again I write down here I is 1 to n, I is 1 to n, I is 1 to n, I is 1 to n. Here's squared. So n times summing up 1 equals 1 plus 1 plus 1 plus 1, and this n times. Hmm? 10 times summing up 1. 1 plus 1 plus 1 plus 1 plus 1. Oh, where's my camera is left? This. Here, I'm back again. Sorry. What happens there? I don't know. 1 plus 1 plus 1 plus 1, 10 times, equals, let's take this one, 1 plus 1 plus 1 plus 1, 10 times, equal, you're still there? 10, of course. So here we have a fixed number. Mu plus mu, or not 10, then of course we have to write here n. Mu plus mu plus mu plus mu plus mu, n times, equals, so mu plus mu plus mu, and this 10 times, equals Hmm? 10 mu, of course. So this equals n mu. And this one, sum over all xi, look it up here. This equals, of course, sum over xi is n times x bar. So at this point, we obtain n times x bar. And then, Heureka, n over n minus 1, sum xi minus mu squared minus 2. This n, of course, we can take out of the bracket. Then we have x bar minus mu. Here we also have x bar minus mu, so x bar minus mu times x bar minus mu is nothing else than x bar minus mu squared, but with this n here. So we obtain 10 times 2 times n x bar minus mu squared, and of course this one, so plus n times x bar minus mu squared. This and this cancels out, and what we obtain is 1 over 1 n minus 1 times, and this is our true parameter. Here we need the expected value. So we obtain our sigma squared minus sigma squared x, the x. Oh, here we still have here an expectation operator. You get this also a bit better typed. So we obtain here expectation operator. The expectation of x bar minus mu squared is sigma squared, now the variance of our arithmetic mean times n, and we know that oops, that variance of the arithmetic mean scales with 1 over n. So in the end, we obtain 1 over n minus 1 equals n times sigma squared minus sigma squared equals 1 over n minus 1, n minus 1 sigma squared. This cancels out and we obtain our result of sigma squared. So this, then I have to put a bit smaller. But you, of course, you obtain also the slides. Save. Okay, this is, of course, a bit nasty calculation. But anyhow, I think for one time you really have to look this up and you have to see how you get there, because otherwise you would not understand what you are really doing in statistics. And we will end with another 5 minutes, I think. Then we take the which one? I think all these, the number 6. Because this took a bit longer than I thought. Let's take now number 6. Why is the arithmetic mean this very central role which has the arithmetic mean? Because the arithmetic mean is not only unbiased, as we have already shown in question 1, it is also efficient. And what was efficiency? Efficiency we had at this point. This was that it is not only unbiased, it is also the estimator with the smallest variance. And this we just want to show in the end of this lecture today. So, first of all, we have, in general, our estimators T is sum AI xi with AI sum is 1, and we want to show that AI equals 1 over A for efficiency. So therefore, we have to calculate the variance of our estimator. For the variance, we know variance of sum AI xi. At first, from our property, A times xi, that in the variance, this takes out with a square. So it is not a linear operator. So we obtain the sum over variance of AI xi equals the sum over AI squared variance of x I, and this that we can move in the variance operator just in here means the reason for this is that all xi are statistically identically distributed and independent from each other. So they should be identically distributed, so they all have the same variance. So we obtain sum AI times sigma squared. And what we have to do now is just minimize this function of AI squared sigma squared sum oops subject to that all AI sums up to 1. And hopefully you see the structure of this problem. Where do you have already seen some optimizing problem? Now, these problems you have everywhere in economics. And maybe in microeconomics you remember maximize x to 1/2 times y to 1/2 subject to, let's say, 10,000 equals 2 times x plus 3 times y. Nothing else we have here, so we can also take the Lagrangian function and then obtain L equals sum AI squared sigma squared plus lambda times 1 minus sum AI. And this is just a function of A1, all AIs, A1, A2, A3 up to AN and lambda. How do you optimize such a function? What are you doing? Well, we have to take the derivatives just due to these variables. So we have to calculate the L, the AI. And what is the derivative? Well, we have here in the sum all these AIs. Taking the derivative with respect to A1, then we are not interested anymore in A2, A3, A4, A5. These are then in the derivative just constants. So all these cancels out. So therefore we obtain 2AI times sigma squared. And here we have also only here the AI. So we obtain minus lambda AI. Oh, not lambda AI because the derivative is just 1 equals lambda. In optimum, this has to be 0. So we obtain AI equals lambda over 2 sigma squared for all AI. Because this we have to do with respect to A1, A2, A3, A4, and so on. And if we do this, we know that this has to be the case simultaneously for every parameter AI. So from this, we obtain AI equals AJ for all I not equal J. And this means all parameters have to be the same. If all parameters are the same and they have simultaneously to sum up to 1, then of course this means A1 AI equals 1 over n, because sum over I1 to n over 1n equals n times 1 over n equals 1. And here we are finished. So thank you very much for listening today, and I stop the recording.